Okay, everybody. First AP Physics C video of the new school year. All right, just a little kinematics review, quick. Mostly graphical here, as that is what the first worksheet has the most to do with. Now, we're going to go through and talk about what a few things mean, but first thing we're going to do here is just going to adjust my camera a little bit. Just kind of talk about a couple of the different graphs. In motion. So if something, let's say a ball is rolling along the ground, all right, it's moving, rolling forward at a nice constant speed. Maybe it's the infamous shoot for your grade lab. All right, so it's rolling along, nice constant speed, traveling the same distance each second. All right. Let's get a little bit of terminology out of the way first. In order to make a graph of this motion, first we have to set a coordinate system. All right. So a coordinate system consists of an origin, so that's 0 meters, and a direction. Right. So this is the positive x direction to the right here. These are cruddy looking arrows, but they're there anyways. So 0 meters, that's a positive x direction. And there could be a scale here, but we're going to keep this conceptual. So the thing here is we assume that each of these pictures is drawn with an equal time interval between each drawing. So if I was to make the position versus time graph that corresponded to this graph, this motion, t is in time, that's going to be in seconds. Position, we're going to use an x, and that's going to be in meters. All right, so the object starts at the origin, and a time interval later, it's moved to the right. It's gained positive position, right? So it goes up on the position axis. So each second, it travels the same amount forward. So if we were to plot individual points, right, of its position versus time, the line would look like that. I'll get rid of that one. All right, and usually we don't plot individual points. We do sometimes, though, when we collect data in lab or we use video analysis or motion detector, we are plotting individual points. Got some tea going here to combat my voice, which is already being lost after one day. But anyhow, here we go. So I guess I should maybe put the units here so we can keep track of that. Seconds. The slope of this line. All right, there's two slopes. There's the slope, well, for a linear line, I guess the slope is the same as the instantaneous. Hopefully I spelled that right. Slope. Because it's, we have this tool called a slopometer, right? This is my slopometer. I can hold it tangent to the line, my position versus time function. The slope of my slopometer tells me the velocity of the object. So in this case, the slope of x versus t equals velocity. A vector quantity, technically, slop. Slope. So the slope of position versus time gives me velocity. And again, when I use my slopometer, sometimes I'm figuring out the slope of the line exactly at some time. So if I want to figure out what its velocity was halfway through its motion, I have to know the slope of the line halfway through its motion. In this case, it's just a constant slope, so there's no difference. All right. It's the same as it is for the whole range of motion. Now, I can make a velocity versus time that corresponds to this. And with a velocity versus time, usually position versus time, we start with, just the one quadrant. Usually when we make velocity versus time graphs, we actually do both quadrants, because if it turns around or heads in the negative direction, we need to have a negative velocity to go with it. And so the slope of position versus time tells me what's going on with velocity versus time, if you remember, right? So a nice constant positive slope. on the position versus time graph, that means a nice positive constant velocity. So literally, I'm holding my slopometer tangent to this line, and as I check it, my slope stays the same, right? Same constant positive slope throughout the whole time interval. So I have a nice positive constant velocity throughout the whole time interval, and then the corresponding acceleration versus time graph, right, would just be 0. No acceleration, right? So slope of v versus t equals acceleration, right? So since I'm in the glare zone here, got to be careful. This light overhead here, I probably should just shift down a little bit. I got a little more space now down here, so maybe I'll try that carefully, sneaky, shift my whole whiteboard down a little bit, see if I can get out of the glare zone slightly. You know, ooh, there we go, Hey, it's a little darker over here, but that'll be okay. Anyhow, slope of v versus t equals acceleration. All right, so hopefully you remember that. Just basic introduction. Let's look at something accelerating really quick. All right, so if something accelerating is, we just use a ball rolling again. So I guess it'd be kind of silly for a ball to just magically accelerate as it moved, but let's pretend it did. All right, so maybe it's like got some crazy thing going on, like BB-8 or something that can accelerate. It's got some sort of drive inside of it that'll cause it to accelerate. Sorry, I gotta have a T here. So this one's position versus time graph, and these are pretty simple examples for advanced physics students to CBA, but we gotta just make sure we get the basics down here. X versus T, right? So this one is classic top opening parabola, right? X is not proportional to the time. It turns out X in this case is proportional to the time squared. We'll talk a little bit more about that later on, linearization of data. So this one's a little bit different because still the slope of this tells us the velocity. Now, if I was to take the slope from beginning to end, like draw a tangent line across the whole thing, the slope of that line would be average velocity over that time, or the average velocity. If I want the instantaneous velocity at a particular time, I have to make a tangent line at that particular time and then figure out the slope of this tangent line. So again, the slope at a particular is a word we like to use in physics. Slope at a particular time is the instantaneous velocity. And the sign matters. Right? If it's a positive tangent line slope, positive slope in the tangent line, it's a positive velocity, and so on. So for this one, and again, I'm just doing this to review. I know this is probably simple for a lot of you, but I don't care. All right, the velocity versus time line goes up straight and linearly. Now, you can't really tell if it's linear just by looking at this graph. Does it really accelerate at a constant rate? Well, that line's kind of drawn poorly, but you gotta be given some extra information there to be able to make that determination. I will tell you that it's accelerating at a constant rate. That is going to matter this year. So what happens here is, why does this value velocity go up? Well, it's because if we were to measure this at set time intervals, right? Slope in the beginning is 0, therefore I have 0 velocity. The slope increases a little bit, so my velocity's got to go up a little bit. Slope increases more on position versus time, the velocity's got to go up a little bit more, and so on. So as that slope of the position versus time graph gets steeper, the velocity of the ball is increasing. All right, so that positive slope on that velocity gives me a positive acceleration. All right, positive constant acceleration versus time. All right, so there we go. Now, one thing we haven't talked about yet is what the area under the curve tells us, right? The area of this triangle, so over some time interval t and some height delta v, right? Total time interval, area equals 1/2 base times height. All right, that's going to give me the displacement of the object. So 1/2 of the base, which is t, and the height is delta v equals delta x. What's kind of cool about that is you can actually derive all the basic constant acceleration kinematic formulas here, right? We know that acceleration, average acceleration, is change in velocity over time, right? So check this out. Solve this for change in velocity, right? Change in velocity equals acceleration times time. Plug that in over here, you get 1/2 of time times acceleration times time equals delta x. You get delta x equals 1/2 at squared. Kind of cool. How do you get the v initial t component there? Well, in this case, that term is just 0, right? Because the initial velocity is 0. In fact, how you get that is if, because you're missing part of it. That's not the full picture. Well, that's because it doesn't look like this, right? So the triangle here is your 1/2 at squared. The rectangle underneath it is the v initial times time. So the full al grande we call the delta x equation. Delta x equals 1/2 at squared plus v initial t can be derived by looking at a case where we do have some sort of initial velocity. And it literally is you're adding the area of the triangle onto the area of the rectangle. And that's kind of cool because, this triangle, the 1/2 base times height plus base times height, I don't know, this just is always kind of a neat thing to me, to think of this geometrically, right? Like this equation, this is the triangle's area, this is the rectangle's area, and you add them together. I just always think that's a really cool result. But anyhow, that's just a little fun thing. Rewind that, check that out again. That's pretty cool. The acceleration versus time graph for this, simply, positive constant acceleration. We already talked about that. Area under this curve is change in velocity. It goes acceleration times time. It's a constant acceleration, so it's just a rectangle. If it was a triangle, then it would be 1/2 base times height. The base is the length of time. The height is the acceleration. All right, so there's all kinds of ways to do this on that first worksheet 0. You're not going to use the kinematic equations. You're going to use graphical techniques. So let's just look at a quick little example here. I'm not going to draw the physical situation. I'm going to give you the position versus time graph. So let's say it's like, I don't know, I think you have one where it goes down like that and it curves off, right? Okay, this is x versus t. So if we try to make a motion diagram for this, right, this is something that's at time 0 starts with a positive position. So it starts somewhere over here, all right? And it moves towards the origin. Now this is always, when I'm saying origin, I don't mean the origin of this position versus time graph. It's the origin of physical reality. It's like if the door of the classroom is the origin, meaning the place you start in the classroom, then if you head towards the origin, you're heading towards the door. So I'm heading towards this location in space, right? And it's a kind of a slow speed for some time. It gets about halfway there, right? And what happens? Well, the slope of this is constant and negative, but then it gets, really steep and negative and starts moving fast. So what happens here is this thing actually starts picking up speed, moving towards the origin. So these arrows have to get longer pretty darn quick, right? So up until about that time, it was moving at a constant negative velocity, but then that negative velocity got fast quickly. All right, so the velocity versus time graph here. All right, we have a nice constant negative slope, fairly low, so I'll transfer this transition time down here. So we have a nice constant negative velocity, and then it actually gets more negative. It actually goes like that, which is kind of interesting. It's maybe a little unexpected. All right, but this video is kind of help you out with that first worksheet. There's going to be some quantitative analysis in this worksheet as well, which really you're going to take slopes and areas under the curve. That's how you're going to do all of these. Okay, so the acceleration here is 0 for the first part, and then I'd say 0, then a negative acceleration. Right? Remember, negative acceleration does not mean it's slowing down. Okay, negative a does not mean deceleration. Okay, it does not mean that. If something's moving in the negative direction and speeding up, its acceleration is negative. So it's kind of hard to think of that conceptually without thinking of the force, right? The direction of the acceleration always follows the direction of the force that is causing the object to accelerate. So if something's accelerating to the left, that means either it's getting pulled to the left and sped up, or it's moving to the right and something's pulling it backwards to slow it down. So a negative acceleration can be speeding up and slowing down. It just depends which direction the object's moving. All right. I think that's going to be enough to get you started. I'm not going to do any math numbers here. I want you to kind of figure that out. This is more like I would have done this in class, just these notes, and talked at you for 17 minutes like we have here, but what the heck. Watch the video. You're going to watch this, over the next couple days in your remote lessons. Okay, guys? Talk to you later.